Hi students, this is Professor Joe Angley, and today in this lesson we'll be learning about systems. As you listen to the lecture, I want you to make sure that you understand a few key concepts. First, you should be able to define what a system is. Second, you should be able to understand and explain the concept of a feedback loop and how it contributes to stability in a system. Lastly, at the end of this lecture, you should understand the concepts of resilience and emergent properties. Let's get started. The idea of systems is useful because it helps us organize our thoughts about the inconceivably complex phenomenon around us. For example, an ecosystem might consist of countless animals, plants, and their physical surroundings. Keeping track of all the elements and relationships in an ecosystem would probably be an impossible task. But if we step back and think about components in terms of their roles, plants, herbivores, carnivores, and decomposers, and the relationships among them, then we can start to comprehend how the system works. We can use some general terms to describe the components of a system. A simple system consists of compartments, also called state variables, which store resources such as energy or matter, and the flows or pathways by which those resources move from one compartment to another. In the figure, the plants and animals represent elements in this cycle of life. We can describe the flows in terms of photosynthesis, herbivory, predation, and decomposition. The plants use photosynthesis to create carbohydrates from carbon, water, and sunlight. The rabbit is a herbivore that consumes plants and uses the energy and chemicals stored there for its own life functions. The fox, in turn, is a carnivore that eats other animals, while the decomposers recycle wastes from all the previous compartments. Understanding the characteristics of ecological systems can help us diagnose disturbances or changes in those systems. For example, if rabbits become too numerous, herbivory can become too rapid for plants to sustain. This could lead to collapse of the system. This is a simplified schematic of a system. Again, note that the two basic parts of a system are 1. Flows, and 2. The boxes that are labeled A through E, which represent state variables. We can also call state variables by other names, including compartments and components. State variables can increase, stay the same, or decrease. Note that the state variables are connected by flows. These flows represent the movement of matter and or energy between the various state variables. Now let's look at the basic types of systems. Open systems are those that receive inputs from their surroundings and produce outputs that leave the system. The Chesapeake Bay is an open system. Fresh water, nutrients, and some organism flow into the bay from rivers, while energy comes from the sun. And other chemicals, water, and organisms, along with the energy they've captured, flow out of the bay into the ocean. In general, all natural systems are open to some extent. In theory, a closed system exchanges no energy or matter with its surroundings, but these are rare. Some biological communities may appear to be closed. For example, a carefully balanced aquarium with just a few plants, fish, and decomposers or detritus eaters may exist for a long time without any input of external materials. But plants need light to survive, and excess heat must be dissipated into the surrounding environment. So, although closed to material flow, the aquarium is still open with respect to energy. Throughput is the flow of energy and matter into, through, and out of a system. We can measure the throughput of materials through the Chesapeake Bay, for example. If 100 million kilograms of nitrogen enters the bay, then ideally 100 million kilograms will be exported. Some will flow out to the sea, some will leave the bay with fish or birds that feed on nutrient-enriched phytoplankton or aquatic plants. Ecologists have observed, though, that this level of throughput supports an overabundance of algae that blocks sunlight in the water column. To return the system to one that includes more fish and oysters, throughput should be reduced to 85 million kilograms of nitrogen or less. This drawing gives a nice presentation of the difference between open and closed systems. As noted, closed systems are difficult to find because while they may not exchange matter, they almost always exchange energy. We sometimes use the term pseudo-closed systems to indicate a system that exchanges a limited amount of matter or energy with its surrounding environment. Positive and negative feedbacks are a fundamental part of ecosystems. Consider the simple system in the figure. A pair of rabbits produces several baby rabbits, and reproduction can lead to greater and greater numbers of rabbits. Positive feedback. If there were an unlimited supply of food, the rabbit population would increase indefinitely. But if the growing rabbit population depletes its food supply, starvation will slow or reverse population growth. Negative feedback. When there are fewer rabbits, the plants recover and the cycle starts again. Multiple loops may interact in ecosystems. Negative feedback loops tend to maintain stability in a system. We often think of systems exhibiting homeostasis, or a tendency to remain more or less stable and unchanging. Your body temperature stays remarkably constant despite dramatic changes in your environment and your activity levels. Changing by a few degrees is extremely unusual. Just think how little temperature change is involved in a serious fever. Natural systems, such as wetlands, tend to be stable too, at least on the scale of years or decades. Over long periods of time, they may change quite a bit, though. Systems might fluctuate. The population of a species in a wetland might rise and fall repeatedly, or in a cycle, and that cycle might be part of the system's normal functioning. Disturbances, or events that destabilize or change the system, might cause the population to fluctuate. Seasonal drought in a wetland, for example, will periodically reduce some populations and increase others. Disturbances might also be large enough to cause more dramatic and persistent change. Drought could lead to fires, which could remove trees but encourage undergrowth for years, decades, or longer. A flush of nutrients inputs, a hurricane, or drainage canals are all disturbances. Sometimes ecosystems show resilience, or an ability to return to their previous condition after disturbance. Other times, ecosystems undergo a state shift, where conditions do not return to normal. For example, rising sea levels could change a freshwater coastal swamp with standing trees into a tidal salt marsh. Some species are adapted to exploit disturbances. For example, tree species that are adapted to bright sun and little shade do well after a forest fire has removed large trees, allowing more sunlight to reach the forest floor. Species such as the pin cherry and the aspen grow quickly in full sun, but do not grow well once the forest has matured. Species such as the pin cherry are called pioneer species. If you think about it, biodiversity depends on continual natural disturbances that allow different species to thrive in different areas at different times. Emergent properties are another interesting aspect of systems. Sometimes a system is more than the sum of its parts. A wetland has complex varieties of living organisms, colorful dragonflies, intricate webs of relationships that can reinforce each other through their complexity. This system has larger influences beyond its borders, helping to stabilize local temperatures and humidity, producing biodiversity that spills over into surrounding areas, or supporting migrant waterfowl. A wetland also has beautiful sights and sounds that may be irrelevant to its functioning as a system, but that we appreciate nonetheless. Consider mangrove forests as an example of emergent properties. Mangrove forests grow along coastlines throughout the tropical world. Because their direct economic value can be modest, thousands of kilometers of mangrove-lined coasts have been cleared to make room for shrimp ponds or beach resorts. But the mangrove forest provides countless indirect economic values. Prop roots trap sediment and stabilize mudflats, improving water clarity and protecting offshore coral reefs from silt. Mangroves also protect small fish and other marine species. Many commercial ocean fish and shrimp species spend juvenile stages hiding among the mangrove roots. And the forest protects the shoreline from damaging storms and tsunamis. Collectively, these services can be worth hundreds of times the value of a shrimp farm, but they exist only when the many parts of a system function together.